Hey there, everybody. This is Mr. Sheeline for. This is going to be the check your understandings for the 8.2 notes, considering or looking over electricity and currents. Then we're going to go through these check your understandings and also this kind of Coulomb's law stuff. So, all right. So in here, first we got to go over Coulomb's law, and Coulomb's law, remember, is the whole bit about the fact that we can measure an electric force between charged particles due to the electrical constant, Coulomb's constant, and then also, also the charges of our particular materials and then the distances between them. So we're tasked in this little guy right here to say, or we're tasked to find out what the electrical forces between these two protons are here, and then what the gravitational force is going to be between the two particles, between the two protons right here. And so we're pretty much given everything we need. We've got the charge, so this right here is going to be that's going to be Q1 and Q2. Okay, so we've got that. We've got K, and we also have R here, and R is going to be 0.001 meters. Okay, we also have R down here as well. R is the same thing, it's 0.001 meters. And we also have the mass right here, 1.7 times 10 to the negative 27 kilograms. And then universal constant, gravitational constant, 6.77 times 10 to the negative 11 power Newton meter squared by second squared. Okay, so, sorry about that. So, all right. So we are tasked to find out what, again, the electrical force is versus the gravitational force. So I'm going to toss this onto a separate piece of paper just so I have a bit more room to work. So, all right, so the first one is, what's the electric force? What's the electric force between the two protons here? Again, if we have Q1 and Q2 equaling 1.6 times 10 to the negative 19th coulombs, if we have K equaling 8.99 times 10 to the 9th power Newton meters squared by Coulomb squared, and then a radius of 0.001 meters. Okay. So, and we've got the equation right here. Fe is equal to K, which is going to be multiplied by absolute value of Q1 times Q2 all over R squared. Okay, and we've got everything. We're searching for this guy. We've got this in the right we got this in the right order, so we can just basically plug and chug. So here's K. K is 8.99 times 10 to the 9th power times Q1, Q2, so it's going to be 1.6 times 10 to the negative 19th times 1.6 times 10 to the negative 19th all over 0.001 squared. Okay. So if we pop that in, yeah. Okay. To make it look something like this, so here's 8.99 times 10 to the 9th power times 1.60 times 10 to the negative 19th times 1.60 times 10 to the negative 19th. We can close all that and then divide by 0.001 squared. We should get this number right here. We should get, roughly speaking, 2.3 times 10 to the negative 22nd power newtons for our electrical force. So here we use Coulomb's law to find out that the electrical force felt between these two protons would be 2.3 times 10 to the negative 22nd newtons. Not only that, it's also repulsive. So this is a repulsive force. So meaning that if we had the proton here, we had the proton here, here it was R, which is 0.001 meters. There's going to be a repulsion force between these two of roughly about 2.3 times 10 to the negative 22nd newtons. And then here is also 2.3 times 10 to the negative 22 newtons. Okay, so that's what we just figured there. Again, this is going to be the electrical force between these two protons. Now, we've got to compare that with gravity, because there's going to be a gravity, even for how small those guys are, there's going to be a gravitational force between them. So we're trying to find F of G. We're trying to find gravitational force. Okay, we've got big G, which is 6.77 times 10 to the negative 11 power Newton meters squared by second squared. We also have the mass of the first particle and of the second particle, which they're the same. So it's 1.7 times 10 to the negative 27 kilograms. Okay, and then we've also got the distance, sorry for the bell. It's 0.001 meters. Okay, so same thing. We have this all set up already. F of g is equal to g times m1 times m2 all over r squared. It's set up to solve for this guy, so we can just plug and chug. So here, and then it's going to be 6.77 times 10 to the negative 11 power times 1.7 times 10 to the negative 27 power times 1.7 times 10 to the negative 27 power all over 0.001 squared. And we can pop that into our calculators to get the gravitational force felt between these two protons. Oops. Then here is, after popping it all in, this is what we should get. We should get 1.9, I'm going to go actually 3 sig figs, 1.96 times 10 to the negative 58 newtons. So 1.96 times 10 to the negative 58 newtons worth of force felt between them. So that's to say this, that we got a proton here, we got a proton here. Here is the distance between them. And it's to say that they are going to have a gravitational force equal to 1.96 times 10 to the negative 58th newtons. Here, 1.96 times 10 to the negative 58 newtons of this attractive force coming together. Okay, a gravitational force. So, but what we see here though, so to write that guy up there, remember, this is what we see. We see that the electrical force is going to be 2.3 times 10 to the negative 22nd power newtons, while the gravitational force is going to be 1.96 times 10 to the negative 58th power newtons. So that means that the electrical force is 36 times greater. Don't need to have that, but it's 36 times greater than the force of gravity. Okay, so when we're talking about electricity, this means that an electrical force is going to overpower a gravitational force. Okay, and this just means that we can also then calculate the particular forces between charged particles within a space. Okay. All right, so then to move on to check your understanding number 1. So how many electrons pass a point every single second if there's a current of 2 amps? Okay, so we're saying, okay, if we've got 2 amps, what's the number of electrons here? It's the number of electrons. So remember, well, we know that for every 1 amp, there's 1 coulomb, and in 1 coulomb, there's 6.25 times 10 to the, what is it, the 19th? 18th. 6.25 times 10 to the 18th number of electrons in 1 coulomb. So we've got 2 amps, so roughly it's just 2 times the 6.25 times 10 to the 18th power electrons, which if we put that in, that is going to give us a whopping 1.25 times 10 to the 19th power electrons. Okay. So again, we would only have, or stuff that we would only, because that's a whole lot of them, but there would be 1.25 times 10 to the positive 19th number of electrons passing through, let's say, an outlet that's pumping out, 2 amps worth of current. Okay, same thing here. Current is going to be 12.6 amps. How many electrons are passing through? Okay, well, again, it's just going to be 12.6 times 6.25 times 10 to the 18th power. Okay. So virtually the same thing here, only now it's going to be 12, and it's going to be 0.6 And so here is going to be we're going to say 7.9 times 10 to the 19th power electrons for our answer. Easy peasy. Sorry for the bell. And then check your understanding. Number 3 is a little bit more difficult. So it's okay, well, what if the current here, or we don't know what the current is. Don't know what the current is. We've got the number of electrons. It's 3.125 times 10 to the 18th power electrons. What's the current? So remember, we know that in 1 amp, there's 1 coulomb. In 1 coulomb, there are 6.25 times 10 to the 18th power electrons. Okay. So how do we go from here to here? Well, we can just use some simple dimensional analysis. So it would be this guy, we got electrons, and we got to convert electrons to amps. So in 1 coulomb, there are 6.25 times 10 to the 18th power electrons. Okay, and in 1 coulomb, there's 1 amp. So really, it's just going to be this divided by this, because this will cancel, that will cancel, and then we'll be left with amps. So it'll be 3.25 times 10 to the 18th power divided by 6.25 times 10 to the 18th power. And then that's going to give me, I messed up there. It should be 3.125. And that's going to give me a nice even 0.5 amps for my current. So in this case, when we're pumping out this number of electrons, that current is running at 0.5 amps. Let's see here. I'm pretty sure that's pretty much all that there is to it in these examples. Yeah, I think that's right. So that's it. That's all that I have here for you guys as far as the check your understandings, and then also the little bit about Coulomb's law right here. So that's pretty much it, guys. So if you still have questions, make sure you reach out to me. If not, I'll see you in the next one.